this video, we're talking about how to find the first-order partial derivatives of a multivariable function, but in this particular function, we have three variables. We have a function f in terms of three variables, x, y, and z. So in previous videos, we've done partial derivatives of a function in terms of two variables, and we've talked about how to do that. Now we're going to expand that definition and find the first-order partial derivatives of a function that's in terms of three variables. And really, the process is just going to be the same as we've talked about before. We're just going to take the partial derivatives of the function with respect to each variable one at a time. So we can just go ahead and write out, we're going to need to find the partial derivative of the function f with respect to the first variable, x. We're going to need to find the partial derivative of the function f with respect to the second variable, y. And we're going to need to find the partial derivative of the function f with respect to the last variable, which is z. So we're going to have three partial derivatives because we have three variables. Remember, when you take the derivative of a multivariable function, you have to take the derivative with respect to each variable separately. So let's start with the partial derivative of the function f with respect to the variable x. Whatever variable that we're taking the derivative with respect to, we're going to be treating the other variables as constants. So in this case, because it's the derivative with respect to x, that means we have to treat y and z as constants. So if we imagine that y and z are constants and x is just our variable, what we can say is that y and z are really just like a constant coefficient in front of this x squared term. In other words, in the same way that if we had a single variable function, for example, f of x is equal to 3x squared, we would say that this 3 is a constant coefficient in front of the x squared. It's a constant and it's a coefficient. Well, y and z are both constants, which means that y cubed is going to be a constant and z to the fourth is going to be a constant. So y cubed times z to the fourth, that whole thing will be a constant. So this is kind of holding the place here of this 3, right? It's a constant coefficient in front of this x squared term. It happens to come after the x term because we order our variables alphabetically, but when we're taking the derivative with respect to x, it's going to act like a constant coefficient. So in the same way that if we would take the derivative here of 3x squared, we would use power rule. We would bring the exponent on the x down in front and multiply it by the constant coefficient, and then we would subtract 1 from the exponent. So we'd get 2 minus 1, and we'd say 6x is going to be our derivative. Well, in the same way here, we're going to take the derivative with respect to x. All we're going to do is bring this exponent out in front and multiply it. So we're going to multiply the 2 out in front. Then we're going to subtract 1 from the exponent. 2 minus 1 is 1. So we're going to get x to the 1, x to the first power, which is just x. So we've got the derivative there. And then this y cubed z to the fourth, that's like the constant coefficient 3. Well, notice here that the 3 just stayed in the derivative. It was multiplied out in front. It got incorporated into this constant coefficient here, so it doesn't go away. So we're going to go ahead and leave the y cubed z to the fourth. Another way to look at this, if you want to, when you're getting used to taking partial derivatives, you can factor out anything that's not related to the variable that you're trying to find the derivative for. So if we were trying to find the partial derivative with respect to x, we know we're treating y and z as constants. Just bring those out in front, factor them out in front, and say y cubed z to the fourth, we know they're constants, and then you have x squared. So you can rewrite it this way, and sometimes this helps people because now they can see this more clearly as a constant coefficient. Then you do the same thing. You bring this 2 out in front, and you end up with 2y cubed z to the fourth x to the 2 minus 1, or just x to the first, so we end up with x. And then you can reorder your variables and say 2x y cubed z to the fourth. So visually, sometimes it's helpful to factor these constants out in front. And in fact, let's go ahead and do that with this example here. We're going to take the partial derivative of f with respect to y. So taking the partial derivative with respect to y, that means we're going to be treating x and z as constants. So just like I did here, you could factor out the x squared and z to the fourth. They're both constants. So bring those out in front and then just have your y cubed here. Now, just like we used power rule here, we bring this 3 out in front, and what we get is 3 times x squared z to the fourth y to the 3 minus 1, or y squared. And now you can just reorder your variables and say 3x squared y squared z to the fourth. Lastly here, we'll take the partial derivative of f with respect to the variable z. So when we're taking the partial derivative with respect to z, that means we have to treat x and y as constants. So this x squared y cubed, they together are going to act like a constant coefficient in front of this z to the fourth. So what we could say is x squared y cubed, we know that they're going to stay. The derivative of z to the fourth is 4z cubed. And then when we simplify this, we get 4, we bring the 4 out in front, x squared y cubed z cubed. And as you can see, we kind of used 3 different methods to find the first order partial derivatives, but we're really just doing the same thing every time. Here we didn't really do any manipulation, we just recognized that y and z were being treated as constants and we took the partial derivative directly. Here we factored out the variables we were treating as constants, we pulled them out in front, and then we used power rule. Here we just left the variables we were treating as constants and we used power rule to take the derivative of the variable we were interested in and then simplified. So it's a slightly different way of going about it. Each one is correct, but that's how you take the first order partial derivatives of a multivariable function.